This is a merge of two different talks that that I've been giving in general. One about the governance, and this is mostly about governance, and another one towards the end, which is more technical, about the smart contracts in Tezos. There's a lot of slides. There's a lot of things to cover. I would also like to take questions, so some slides I may just slide over so that we can have a chance to have more of a chat than just a long, boring presentation. Okay, so for those who don't know, Tezos is a self-amending ledger. What does self-amendment means? It's a word that comes from philosopher Peter Suber. It's the idea of a system that can change itself from within. And Peter Suber was specifically interested in mathematical systems, which can have proofs about themselves, or sometimes can't in interesting ways. But also governance, legal documents like the US Constitution. Is it possible to have a coherent system that can completely change its own rules? And it came to the conclusion that yes, it was. And so a blockchain is a set of rules, and the question is, can you embed in a blockchain the rules for its own modification? And so that this is what we're about, self-amendment on a blockchain. So I'm going to talk a little bit about that. A few words on soft forks and hard forks, shelling points, and how all of that relates to governance. Okay, so what is a blockchain? So a blockchain is a concurrent data structure, and it's concurrent because many people access it at the same time. And if you ever written multi-threaded code which share data, it's difficult because you need to have some sense of who owns the data, who's accessing it, unless you're using data structure where you're only adding data, right? If you just have different threads or different people, they just add data to the structure, they don't change anything, they just add more to it, then it's easy to be concurrent. So the blockchain is this append-only data structure. And what do you use it for? Well, so you have this structure which doesn't have mutation. You don't change anything, you just keep adding. But essentially what you want to represent is mutation, right? You want to represent the fact that I had some tokens and you didn't have tokens. We had a transaction and now you have tokens and I don't have tokens. So something changed, and it's a way of representing change. So mutation, it's shared because we all want to know about that. And it's a singleton in the sense that there's only one version that exists. And the way we do this is instead of representing this state like you would on a normal program on a computer as a database where you can just change something, you're going to have a linked list of operations, right? So you have an operation that says how things have changed, and the state is implicit. You just look through the operations. Okay, so this is the trick. For those who like functional programming languages, this is actually a monad where you represent a state through a series of changes. So in Bitcoin, for example, what is the state of Bitcoin? It's the state of all unspent outputs. It's everything that's not been spent. Plus, you could add some state variables like the total amount of work that's been done on a chain, the current difficulty, the timestamp, etc. And the operations are the transaction. And so in general, any blockchain algorithm can be defined by a state transition function, which we call apply. It takes a state, it takes an operation, and it gives you a new state. So that's every blockchain algorithm. And so the problem we have with just this is since everyone can access it at the same time and just add data to it, your list is not actually a list, it's a tree, because people could just they can add blocks wherever they want. And so you need to have some ordering over the branches of that tree. You need to be able to pick one branch and say, that's the right one. So we could have a variable where we say, that we overwrite each time and say, yeah, this is a head. But then we just, have reintroduced mutation, so that's still not good. And so in order to do that, we're going to have some sort of consensus protocol that happens inside these blocks. And from that, we're going to be able to derive a score function. And the score function is something that tells you which branch is better than which other branch. And so all existing blockchain implementations have this structure, a state transition function, and a scoring function. And this is true of any design you have here. You can imagine even sharded blockchains or even more like centralized versions or meta blockchains, what have you. They all have essentially this structure. And so how do you implement this score function? Well, in Bitcoin, you look at the total difficulty of the branch. So it's sometimes by a small abuse of language, it's called the longest branch, but it's actually the one that had the most hashing power. So you just say that, and this is the one branch that will work. And incidentally, what you're doing in proof of work is that you're actually doing real life like mutation, because you're wasting energy with your miners, and you're releasing heat, and so you're actually like doing something irreversible here. You could have a centralized model where you have just third parties sign the branch. And you can have something like proof of stake, where you are going to validate or count signature from some set of people who have been authorized to sign the blocks. So how do we have a self-amending blockchain? Well, we take these functions, apply and score, so they describe a whole blockchain algorithm, and we're just going to put them inside the state, right? So now our state, instead of saying you have 10 tokens, you have 20 tokens, you have 50 tokens, now the state says you have 10 tokens, you have 50 tokens, and by the way, this is our transition function, and this is our scoring function, right? So if you do that, now your state can evolve. Now your blockchain contains its own laws, and it can look inside its own laws. So that's introspection. So what about hard forks and soft forks? So sometimes people will tell you, well, you don't need to have this type of on-chain governance. You don't need to just like auto-upgrade your protocol. You can just do a hard fork, right? You can just tell everyone, hey, we have a new version, and we're just going to run this new version. Why go through the weird exercise of trying to do this inside the blockchain? So a few definitions, the difference between hard forks and soft forks. So they're often presented as being different. They're actually pretty much the same thing. So a hard fork, the participants agree to change the rule of the protocols, and so now they have a completely new protocol. And the key difference is that there are blocks which used to be invalid, and now they're valid, right? And so, for instance, if you look at Bitcoin Cash, it's a hard fork because it has blocks which were bigger than were previously allowed, and therefore, some blocks which would have been considered invalid are now valid. And in a soft forks, what you do is you just restrict the set of valid blocks. You say, now we can only have, the blocks can have a certain form. So someone who hasn't upgraded their software, they're going to seize these blocks, and they're just going to accept them because they're like, yeah, it's a valid block. But you can change the semantics of it. So SegWit in Bitcoin, for example, is a soft fork, because for someone who runs the old version, it looks like you have a transaction which does something weird and crazy, but for someone who has a new version, it looks like this transaction has a meaning, right? And this is why the difference is largely academic, because let's say you want to do a block size increase with a soft fork, right? What you could do is you could say, well, actually, we're going to have a regular block, and we'll put in a transaction which will point to a hash, and then magically on the network, we're also going to pass larger blocks which will have this hash, and voila, we have a block size increase with a soft fork. So pretty much everything, apart maybe for changing the hash function in your proof of work algorithm, and even that, you could just drop the difficulty and add another hash function. So pretty much anything that you can do with a hard fork, you can do with a soft fork. So the difference is really just enter on the pinhead territory. But what they have in common, when you do a hard fork or a soft fork, you can still have two versions, right? You can have, in a soft forks, you can have people ignore, they could ignore the semantics of those blocks. In a hard fork, they could completely ignore the blocks. And so what fork is going to win? And if you go back to 2014, a very proof-of-work centric world, when people were talking about this, they were saying, well, obviously the one with the most hashing power, right? This is why Bitcoin has value, is because of all this hashing power. This is why you can't, you can't possibly just copy Bitcoin, because if you did, you wouldn't have all this hashing power, right? It's a resource that can't just be copied. I can't just have twice the hashing power if I have 2 Bitcoins. And that's wrong for many reasons, one of which is there's no laws of economics that says that, if you have the most hashing power, you have value, and if you have, n-1, then you have no value, right? So clearly you need to have enough in proof of work to have some level of security, but at some point you hit diminishing marginal returns in your security. So it's not that, and also hashing power, the miners have electricity bills to pay, they're going to follow price, right? They're not just disinterested participant in the governance who are going to say, well, this is what we prefer, we're going to hire this. They're going to follow the price. Okay, so what is going to determine the price? Well, is it the one that the users adopt? Is it, they've been talked about user-activated soft forks where the user installs software and they say, well, we're only going to look at the blockchain a certain way. So, okay, maybe it's the one users adopt, but is it necessarily the best one? And the truth is, the fork that wins is the one that everyone expects to win. It's very circular, right? Let's say there's a fork and you presented, you had 1 coin and now you have 2 coins. And you're going to say, well, great, I could just be risk averse and sit on both and see what happens. However, there are some people who are going to think, well, one of these coins is going to capture most of the economic value. And the reason for that is just network effect, winner-take-all effects. So one of them is going to capture most of the value, and in this period of uncertainty, where maybe no price is formed, I can arbitrage this by selling the one I expect to fail and buying the one I expect to win, right? And every person using the system has the incentive to do the same thing. So you have a sort of information cascade where everyone is just trying to predict what everyone else is going to do, and they all tend to they win if they make the same prediction, essentially. And that prediction is not going to be which one is best, it's going to be which one is going to win. So why does this why does this matter? Why should we try to think about hard forks? After all, why not just hard fork? Competition is good. You're going to have 2 blockchains, they might be slightly different. One will have benefits that the other doesn't have. It's great. We have competition, and maybe the best one will win. Maybe we can have a blockchain for everyone. Let's everyone run their own token, run their own blockchain. Everyone issues their tokens. But economics really favor one chain, especially if you're trying to do something like money. In most theories of money has value because it's a liquid medium of exchange. You hold money because you expect other people are likely to also want to hold money, and so it will be a very liquid way of exchanging things. And stuff like Bitcoin, there's a lot of angel and pinhead territory where people will tell you, clearly, Bitcoin is not money because it's not well accepted, and because it's volatile and so on and so forth. It's terrible money, and it's the whole point is that maybe it will be money. Like that's the interest of this thing. It's like maybe they get to be money, and so if they do get to be money, the economics really favor one chain. And so if you just go through hard forks, there's 2 things that are going to happen. First, you're going to have some costly destruction. Why? Because if you have a hard fork win, then the people who make the wrong prediction about the hard fork, or the people who get out-competed, let's say instead of a hard fork, you even create a whole new blockchain, then all of a sudden, all of these efforts are kind of wasted. And so that's destruction. And then at some point, it ossifies. The incumbents become so big that you cannot possibly displace them by competition, in which case now you have stagnation. So, neither very costly destruction nor stagnation is good. We need a way for blockchains to be able to evolve, to integrate innovation, and they need to be able to do that while remaining decentralized, because that is really part of the value proposition of this whole exercise. And they need to be able to do that without having the hard fork dynamics where you are just winning a beauty contest. So one way to explain this dynamics is there's two games in game theory. One is called the Battle of the Sexes, and the other one is Game of Chicken, and they're almost the same game. So in Battle of the Sexes, this is a payoff matrix. So you have a husband and a wife. The husband wants to, in this example, he wants to go to the theater. He gets 3 points. If they both go to the theater, wife gets 2 points. The wife wants to see the baseball match, and she gets 3 points if they go see the baseball match, and the husband only gets 2 points because he would rather go to the theater. And if they all go their separate ways, they don't get any point because they really enjoy doing things together. And in that game, the way you play that is you have to essentially lie about about going your separate way. You have to try to convince that no, you know what? I'll go to the theater no matter what. I'll go to the baseball no matter what. And then try to really force that position and then switch at the last minute. And this is the same thing with the game of chicken. You have two cars running at each other, and you're trying to convince the other one that you're crazier and that you're not going to swerve. And at the last minute, the first person to swerve loses. And you have the same thing in a hard fork. Most of the time, the people who hard fork, they don't want to hard fork. What they really want is they want to change the rules of the blockchains, right? And they threaten to hard fork as a way to push those rules, but you have to make this threat credible. And at some point, the only way you're going to make that threat credible is to make enough pre-commitments that you end up actually doing it. And I think this is destructive in general. So we don't want cars crashing with each other. So one more time. So who's going to control that? So I was saying, is it the users? Is it the miners? Is it an algorithm? It's certainly not an algorithm, right? One example I'd like to give is, Bitcoin has 21 million coin. 21 million is not a mathematical constant. It's not a physical constant. It's human chosen. So that tells you there's a human-driven system that enforces that number. It's not enforced by mathematics. So it's not an algorithm. These things are political systems. Core developers have oftentimes a lot of clout, and clout can translate into political power. And overall, what you have is a kind of a mix of all this. You have a Schelling point. I've been dancing around this concept of Schelling point in the past few slides. It's this idea of making a choice where you're going to win by having the same coordination as everyone else. And everyone else has some idea of what is legitimate. Everyone else has some idea of what is the right chain. And it's very fuzzy. It's not based on hashing power. It's not based on any of this. And this idea, this social consensus, it can be explicit or it can be implicit. And what we have currently in blockchain is we have a very implicit social consensus, right? Everyone kind of understands that a certain blockchain is a canonical one and the other one is a fork, right? Of course, the smaller fork is always going to debate that because you win these games by legitimacy. But in practice, right? And the prices tend to reflect that. So, okay, I have a slide explaining Schelling points, but I'm just going to go through it. Okay, so how does governance? So what do we do in Tezos is we try to have explicit governance, and there were two phases. I think there was a phase of denial, 2014 to 2016. Where people would say governance is not a thing, this is a technical project, all the decisions are engineering decisions, there's no there's no governance. I even remember a prominent figure in Bitcoin saying, there's no governance in Bitcoin. Anytime there's a question, what we'll do is we'll assess the options and we'll pick the best engineering solution. And this is great if you can do that, but obviously, you have a political, who's going to pick the best engineering solution? Like, there's always disputes. And you can have all this implicit governance, but if you have implicit governance, your power can be held in a more insidious way than if you had explicit governance and you know exactly what's going on. So the way we make it work currently in Tezos is the following. So you propose an upgrade, and that means very literally you have a piece of code that you write. So you write your own apply function. You send it to the network. And then you probably want to communicate about it. So maybe you set up a website. You say, hey, I have this great proposal for Tezos, and this is an upgrade. And so many people might propose upgrades in a voting cycle. And we start with approval voting for selecting an upgrade. And so approval voting is a very robust method of voting. All voting methods are flawed, but there are people who are actually running like benchmarks, like make simulations to see which ones are least problematic. And approval voting generally wins top place. And it's very simple. You look through all the upgrades and you say, I like this one, I don't like this one, and so on and so forth. Then you choose the upgrade which has the most approval, and now you submit that to a vote. And then once you vote for it, you have a supermajority voting. So we need 60% of the votes with a 60% quorum. Now sometimes people ask, well, you don't need 60%. What does this 60% mean? Because 50% of the network can control the chain, and so if 50% really want something to happen, they will make it happen. And so it's completely illusory to think you can do a 60% or 70%. And I think that's missing the point, because there are many people who are not willing to do a 50% attack on a network, but who are still willing to vote, and who are still willing to say, hey, we're 60%, and we don't think that's enough in order to push this idea. Maybe we need to convince more people. That doesn't mean that they lose their vote because they have 59% of the vote instead of 60%, and then they go and say, well, we didn't get the vote, but we had 59%, so let's 50% the network. No, that doesn't happen. So the vote is more about creating common knowledge among people, like making it known who supports it and not support it, rather than try to enforce things. However, it is enforced automatically, and the reason for that is that if you don't build in your upgrade mechanism in your blockchain, very simply, people will not. At some point, people stop upgrading. Right? At some point, most systems do not have an auto-upgrade capability, and the proposals just fail by the virtue of laziness. The default becomes not to upgrade, and you can get stuck. So you really want to have this automated upgrade ability. We have an existing quorum, so that if no one votes, the quorum reduces. And a veto mechanism. So the one that's been proposed for the first year of Tezos is to have the Swiss-based Tezos Foundation do a veto. There's other mechanisms to do that. One is to have some sort of elected body. You randomly elect. You elect 20 coins and say, okay, you get a veto power. Or you could have some sort of sortition. You randomly draw a certain number of people, and they can veto. I really like vetoes because they are very asymmetric in their power. Someone with a veto, in general, it's a lot worse to have a very bad upgrade than not upgrade at all, right? Overall, lagging a little bit in innovation, even if you like by a year or 6 months, is much better than just having a disastrous upgrade. And so if you have someone who has a veto and who is evil, the worst thing they can do is they can delay things for a while, whereas the best thing they can do is they can find an upgrade which really came into existence by a fluke, which is really bad, and kill it. And so veto is very, it's kind of a free lunch in terms of governance, veto power. I really like it. And so what happens to the losing faction? So, the people who voted and they didn't get what they wanted, are they going to fork? Well, no, I don't think they're going to fork, because basically it's like you played the game of chicken without actually playing it. you had it's like having some sort of playoff of like, what would happen if we went and had a fork, what would be perceived as legitimate, what would win, and they realized that they wouldn't win, and that they would be in the minority fork, and that they probably don't want to try that because they're actually going to hurt the system in themselves. So it's the idea of it's the idea of democracy as some sort of peaceful revolution where people just get, you don't necessarily vote because the majority is going to be right, but you vote because you would know in a conflict who would win, essentially. So it's kind of more of a way of avoiding a costly conflict than of guaranteeing that you're making good decisions. So what else can we do? So there's other methods. We start with voting because it's very easy to implement. Representative democracy, where you elect bodies, and maybe they can have influence not on the whole protocol, but on small parts. Constitutionalism. So this is an idea where you say, we're not going to vote on just anything. There's some things we don't want to vote about. For example, maybe you don't want to vote about the content of contracts or the balances of contracts. And one of the reasons for that is, if you're using a platform, it's great to know that there's governance on this platform that's going to, say, guarantee that it's going to stay up to date with innovations. But it's not great if you think that this platform tomorrow might rewrite the contract that you're using or might take your tokens or do all sorts of things. And so constitutionalism can enforce that by saying, if you write an upgrade, it needs to contain a formal proof, a mathematical proof that is going to preserve certain properties. So you could preserve properties around inflation, around touching contracts, and a bunch of other things. And the one I'm pretty excited about, and probably something that can go in V2 pretty quickly, is future key. So in future key, what you do is you run a prediction market in order to try and decide which option is most beneficial. So instead of voting, instead of saying, I think that this is the most beneficial option, you have people betting. You say, I bet that this is I bet that if we adopt this, the metrics that we care about, and you can define a whole bunch of metrics. It could be throughput, for example. It could be how many people are using the systems. It could be some external oracles that tell you if something was good. So you bet on those metrics, and betting markets tend to be, on average, more rational. They tend to make better prediction than just making a poll. And the nice thing is you can combine future key with a veto. So you can have future key. You can have all these markets say, hey, this is probably the best proposal, and then you run a sanity check by just having a veto and saying, okay, markets have selected this proposal as being very good. Is it crazy? You have a veto round. So that's a fairly, that one is not too hard to implement, and I think is a fairly good improvement upon democracy, especially since it does not require large participation, right? You don't have to have everyone involved. It can become really specialized. It can become professionalized into a subset of people who specialize in understanding how these upgrades are going to affect the system. So future key is probably something personally I'd like to work on for future versions of Tezos, but obviously that will happen only if there's a vote for it. That's how this thing works. So it's interesting, we can vote outside of the voting system. We can vote for a system that's not voting. So why? So explicit governance is like having a rule of law. Rewarding innovation. So it's still the case today that if you have a really cool idea for a blockchain, you start your new blockchain, right? So there's a lot of interesting projects out there. There's some of them have been built around new consensus algorithm. Take, for example, Algorand has a cool proof-of-stake consensus algorithm, and they're building a blockchain. And so many people are building blockchains, but I don't think we're headed to a world where we have 1,000 blockchains competing, realistically. And I'd rather that when people have a really good idea for an improvement to the state of the art, they can get rewarded for contributing to an existing platform, right? Because today, if you have an idea for how to make Bitcoin much better, your best case scenario is that you're gonna talk to you're gonna gain enough clout in the Bitcoin community and Bitcoin developers, and you're gonna convince them to really support that idea, and you're gonna implement it, and you're gonna get glory, and that is the best case scenario. And your other option is to start a new coin or hard fork, and then actually get it done really and get it done really quickly. And that is currently a much better option. So I want the option for people who are very innovative. I want that their option is to actually contribute to something that exists and improve the network effect as opposed to compete. And solving collective action problems, there's other things we can do with governance other than rewarding innovation, although that is a collective action problem. Evangelizing, you want to use everyone benefits from people knowing about the project and contributing about the project. So it's something that can be done with governance, maintaining, building infrastructure. All of these things are offshoots of governance. Okay, and so the second part of the talk is going to be about Michelson, the smart contract language on Tezos. Well, big change about the governance. In the first version of Tezos, we're a smart contract platform, and we have a language for smart contract called Michelson. And we depart from other smart contract platforms. We have a very different approach in our design. And our design goals were we wanted to have a language that was generic. So there's platforms who have said, we need a domain-specific language for smart contracts because they're too complicated, the Turing completeness is too dangerous. All these contracts, they're all financial contracts. Let's have a DSL of financial contracts or other contracts and run that. And that may be fine, but then you end up with a blockchain that runs financial contracts, and the day you want your blockchain to verify an SPV proof for another blockchain, or for a shard that you create, or for a sidechain, then all of a sudden your smart contract language cannot do that. So you want something that's generic because smart contracts can do a lot more than just contracts, right? They're a way for a blockchain to interact with programmatically with the external world. You want to be able to do everything you want to be able to do. It needs to be safe because writing smart contracts, there's a lot of money behind smart contracts, and bugs can be very costly. And there is knowledge in the programming language theory about, and it's really empirical knowledge about design elements of a language that can make it safer in practice when people write it. We want it to be readable so that if people introspect the blockchain, they can actually see what's going on. They can read the contract and know what happens. And we want easy gas accounting because we still need to monitor how much resources the contract is taking, and so we want to be able to count every step. And now there's a tension here because on the one hand, if you want something generic with easy gas accounting, then it sounds like you want something like assembly, right? So that's what Ethereum did when they had the EVM. And that is also, other projects are either using the EVM or WebAssembly or LLVM. It's very attractive because it's very generic. Why not have an assembly? If you like all these safe languages and general languages, you can just compile down to assembly, and then you're golden. Aha. But then your language is not readable. You can't read it on a blockchain. Well, that's fine. You can just attach the source code. Yes, but now you need a deterministic compiler, and you also need a verified compiler, and it gets trickier. And in practice, if you have an inherently safe base, then all the languages that are going to be built on top of it are going to kind of inherit this safety. Whereas if you have really untyped assembly, everything is possible, you can build inherently unsafe languages on top of it. And so this essentially gave Michelson, which is a compromise. It's a low-level language, but with high-level primitives. So low-level because it's a stack language like Bitcoin, which makes it easier to compute gas. So there are no variables, just elements on a stack. It's statically typed, which is a high-level thing. So we have type for maps and lambdas and timestamps and amounts. It's functional, and it kind of looks like Lisp. So it's it's really a mix of many things. And this is Michelson. It's pretty small. This is Michelson on a postcard. It could be smaller, but we want to give high-level primitives. And so to give you some sense of the data types you have the usual suspects, true and false, pairs for pairing data, left and right for making union types. We have an option type. And then we also have, I think it's interesting, an amount type, an amount of Tezos token. Now, that amount is an integer, but hey, why not type it? Because at least, maybe now we avoid some errors in the contract. We have integer constants, natural number constants. We do not have integer on, we don't have like 8-bit integer or 16-bit integers. We just had arbitrary precision integer. And that was a design choice, and the reason was, so the library we use behind the scenes is libgmp. The overhead when you sum small integers is minimal because it actually recognizes that they're small and calls the processor for doing that. And the benefit is you're never going to have an overflow error when you're in your Michelson contract. It makes gas calculation a little bit harder because you need to make sure you keep track of the length of your integer, but not much harder. And if you looked yesterday, in some ERC20 contracts, there was a vulnerability based on an overflow on integer. So this is one example where you lose a tiny bit of efficiency, but you're really getting potentially a lot of safety in the contracts that you write. List of common stack operations, and then a few interesting advanced types like lists, sets, maps, lambdas. You can have a lambda. So for those who may not be programmers, a lambda is it's an unnamed function. So you can have as a type an entire function. Here's one cool thing you can do with a lambda. Let's say you write a smart contract and you want to update it. Well, one thing you can do is you can have all the logic of your contract in a lambda and put that in your storage and have a multi-signature setup for just changing that lambda. You could even pass that lambda to another contract. So can you do this in Ethereum? Yes. So the way you would do it is basically create 2 contracts and then change a pointer to which contract you're using. It's a lot more cumbersome, and it's inherently less safe because you lose a lot of guarantees. You don't know what the other contract is doing. You need to remember a lot more state in your head as a programmer to understand what's going on. Very easy to do with a lambda. So we're trying to give these high-level primitives to programmers. And down the pipeline, some of the stuff I've been working to add to Michelson are cryptographic primitives. Points on elliptic curves. For example, a PVSS module for people who want to generate randomness in their contract. So there's a whole lot of very high-level primitives that we can give. And we don't have the efficiency of just compiling down to assembly and saying, you know what, we're just going to compile all of this and it'll run on the CPU, and that way we don't have to curate the opcode. People will just write whatever they want to write. Yes, but we kind of know the type of contract that people write. There's not 100 different contracts on Ethereum. There's basically 2 smart contracts. They're ERC20 tokens and they're multi-signature contract. And CryptoKitties, and that covers a lot of the contracts. So people are going to write more interesting contracts, or sorry, I should have also said there's Oracle contracts, there's there's Bitcoin SPV contracts. So all of these interesting contracts, we still have some idea of the type of primitives that they use, and I think designing a language around the primitives, which are useful for typical smart contracts, is more viable and safe than just having a very low-level assembly. So here's an example of Michelson. This is it's got at the bottom. So this is a simple contract for a vote. So in this contract, you have your storage is a map between a string and a number. So the strings are going to be tacos, baguette, or sushi here. And the number is how many votes it got. And so in this example, you start by grabbing the amount that was sent to your transaction. As sent is just an annotation. It makes it easier when you program in an IDE in order to see what you're doing. You push the number 5. You compare the two. If you receive less than 5, you fail. Otherwise, you do a lot of stack manipulation. So this is the ugly underbelly of Michelson, is that you end up doing a lot of dup, deep, CDR, dup, and so on and so forth. But there are macros which can hide that. Then you look in your list, and if it's not in a list, if you're trying to vote for something that's not authorized, it fails. Otherwise, it adds 1, and then it returns. So that's a contract in Michelson. It's not like it's not the most readable thing. If you look at it, especially as a non-programmer, it's going to look fairly arcane. And it's certainly more arcane than looking at a piece of Solidity. But compare that to a piece of EVM or even to a piece of Bitcoin script. If you sit down and you're trying to understand what the contract you're sending tokens to is actually doing, this is much easier to analyze. Okay, and so last part of my talk, I'm going to talk a little bit about a concept I called simulatability. And simulatability is the ability to know what's going to happen when you send a transaction to the system. And in Bitcoin, that works great because outputs are either spent or unspent. And so if I send a transaction, maybe it's going to fail, but if it succeeds, I know exactly how it's going to succeed. I know exactly what the next output is going to be. And so as a result, you can simulate your transaction. If it's valid, it's predictable. And on top of that, this Bitcoin UTXO, it belongs to someone, right? Typically, you can have a UTXO that's shared by maybe 4 people if it's a multi-sig. And so maybe you're doing a multi-sig and unknown to you, the other signers are also doing a multi-sig, and so now you can't really send it, but you have some ideas. And as a result, since the UTXOs belong to people, your transactions commute, right? If I give you 2 Bitcoin transactions, they're not spending the same UTXO, and since they're not spending the same UTXO, you could exchange one for the other. It doesn't matter in which order they are. And we'll see that's a very useful property. Okay, what about smart contracts? So in Tezos and Ethereum, the effect of a transaction is a lot more ambiguous. So another little Michelson program. And basically what it does is it has a flag to see if it's been called or not. And if it hasn't been called, then the first time you call it, it's going to grab 10 tokens and send them back to you. And if it's been called, if it has been called before, then it's going to only send you 5 tokens. And so when I send my transaction to the network, maybe I'm getting 5 tokens, maybe I'm getting 10 tokens. I don't know. It depends on what someone else is going to do with the contract. And fundamentally, the problem is that now we're not dealing with a UTXO. We're dealing with a contract which belongs to anyone who can call it. It's shared by everyone. And since it's shared, you're losing this property that your transactions don't overlap. You have potentially overlapping transactions. So other source of ambiguity, race conditions. So as I mentioned, what is the first transaction that's going to happen? And gas cost. You cannot predict gas costs in Ethereum or even in Tezos. Why? Because if there's a contract which has a big map and you're sending a transaction, and before your transaction reaches that map, someone adds an element to it, now you need more gas, and you didn't know that exactly. So that's annoying. We want to be able to know exactly how much gas we're going to use. We want to know exactly what's going to happen if we send our transaction. And this is especially useful if you're trying to scale with non-interactive zero-knowledge proofs of knowledge, like SNARKs and STARKs. So one article I wrote a while back was on scaling with zero-knowledge proofs. And the way you can do that is, instead of publishing all these transactions and computing all these smart contracts, what if instead we could just run these things on our machine? Maybe I run it before I submit a transaction, or the miner runs it, but at the end of the day, they just present a proof, and they say, that was the old state of the system, this is a new state of the system, and here's a proof. And that proof can be read in constant time and can be verified in constant time, and it guarantees that everything was valid. So that would be great, because now there's no more gas, right? I run my contract, on my machine, and I send the miner a proof. I said, hey, I ran the contract, it worked, here's the results. But that doesn't commute, that's the saying, because the key part to making this work is I have to be able to run a smart contract on my machine and know what's going to happen. And I don't, because it depends on other transactions. So how does that even work in Zcash, right? How does Zcash do it? Well, in Zcash, when you send your shielded transaction with a snark, you also reveal a set of numbers which correspond to UTXOs, and it will not accept two transactions which overlap in these sets of numbers. Right? So the way you're doing it is that you're explicitly saying, I have this whole hidden transaction, and you don't know anything about it, but it touches this hidden part of the state. And another one will say, I touch this other hidden part of the state. So you basically carry with you a proof that you commute with everyone else. And we really want to have this property, and it seems harder to get in smart contracts. So is it because of UTXOs, right? Smart contracts are accounts, and UTXOs are great. They're counterintuitive. So first of all, if you understand how a UTXO works in Bitcoin, and most people do not, then you can be right and it can be wrong, and you can say, haha. This is actually how it works. But they're not magic, right? They're not better for replay protection or all of these things. This is bollocks. They're basically a UTXO is the same thing as a balance account and a smart and a nonce, right? If you have an account and a nonce, it's the equivalent. You have a UTXO, you have a new UTXO. You had an account with a counter. You have a new account with a counter. The only difference is that it's not hash-based, but everything else you can do. So is a difference because we have UTXOs? No. Is it because we have a rich state? So smart contracts, UTXOs are binaries, they're spent or they're unspent. Smart contracts have a state, which is more complex. They can have data, they can have conditions. But it's not really the rich state, right? If we wanted to replicate the UTXO behavior fully, instead of just increasing the nonce every time you do a transaction, you could do it internally every time there's a sub-transaction. So anytime someone touches anything in the contract, you just increase the nonce. And so now, if I send my transaction after yours, then it won't be valid in the same block because we didn't lock on the same value. So the way it would work is you would lock on the smart contract. You would say, I'm sending this transaction, but only run it if and only if the contract is in this very exact state. And that works, right? If you start doing that, then you can commute again. But the problem is, there's a lot of transactions that do commute and that are not going to commute, right? So if I have an ERC20 token or the equivalent, and I send a transaction to spend mine, and you send a transaction to spend yours, they commute. Yes. But if we're trying to be very, very strict about it and say I'm sending my transaction only if the entire ledger of this ERC20 token is exactly like this, then they're not going to commute, and we lose a ton of scalability. So that's not great, right? That's what I'm explaining here. So operations that would normally commute become invalid, and you can't have ERC20 contracts, DAOs, and so on and so forth. And we might want some of those. So what can we do? Well, one option is you could have the smart contract itself tell you if transactions commute. You could send a transaction and say, execute my transaction, but only if the smart contract calculates that it can commute with some other one. And that puts more effort on the smart contract designer to actually say, yep, these two are independent, or they're not independent. And then you would say, only execute my transaction if it's not in conflict with any other transaction in the block. And the validator, the baker, would ask the smart contract if that's the case. Another one would be to do fine-grained taint analysis. So instead of locking on the entire contract, you run a transaction, you see exactly which part of the state it touches. You run another transaction, you see which part of the state it touches, and you can detect if they ever access the same data or if they're dependent on the same data. You can actually do that at runtime, and if you detect that they would have executed the same regardless of which orders they were in, then they commute, and that's great. But you still don't have the proof that you wanted. And the third one, which is less, there's less computer science to it, it's simpler, but it's also potentially more powerful, is all these common patterns, these ERC20 tokens or these DAOs. It's a common pattern. It's basically a sub-token. And the idea is that right now, this approach is representing sub-token in a big shared contract when fundamentally a sub-token is not something that's really shared, right? There's really ownership over each little piece of token. And so if instead of representing these sub-tokens in a smart contract, you have a concept of them at the protocol layer. If your protocol natively understands what a token is, then your protocol can understand that certain operations are going to commute versus not commute because the contract state doesn't look like this black hole that you either touch or not touch. The protocol is going to understand the granularity of transaction on some tokens. So essentially, these are my current thoughts on commutativity, and I think that the way we get it essentially is to try to avoid having this giant contract with a lot of states. We want to put a little bit of states in contract that's useful, but not, if possible, not giant maps. We want to put this as a protocol level, and we want to make sure that we write transactions which are as independent from each other as possible. Okay, so quick summary. This is an old slide, sorry. Tezos is a self-amending ledger. We have governance and innovation by self-amendment. That link is probably broken as of a few days ago. But for those who don't know, Tezos has a beta net. Tezos has an alpha net and a zero net. You probably want to try this script and call it zero net. It's our test net. It's been running for over a year now. People are building cool applications on it. I encourage you to do so. All right, so that's it for the presentation, and I will take some questions.
Thank you, Arthur. That was fantastic technical overview. Round of applause. Thank you. So, are there any questions for anyone? I will run around with the mic. If not, we'll make our own up. Here we go.
So is it possible to create some compiler to the Python to the Michelson and without losing your functional or attribution?
Yeah, so it is possible to write compilers for high-level languages down to Michelson, and there's a few that exist. There's three that I know of. One is Juvix. It's by Christopher Goes. It's a Haskell to Michelson compiler. There's Liquidity, which looks a lot like OCaml and also compiles down to Michelson. Nice thing about Liquidity is you can also go backward. You can take a Michelson code and then compile it into some readable Liquidity. So that's pretty cool. And there's also Phi by Stephen Andrews, which look a little bit like JavaScript. So yes, you can write Python. There was, I know Milo for a while was trying to write a, sorry about that. Milo for a while was trying to write a brainfuck interpreter. That's essentially a language that's kind of like a Turing machine. So you can compile anything down to Michelson, but I hope that people make use of the typing in Michelson, and it's more natural to compile typed languages down to it. So one target I like is Swift. Apple Swift. It's in terms of syntax and usability, it feels a little bit like a Python, but it's typed. So that would be a good target language for not exactly Swift, but like a subset of Swift or something Swift E to compile down.
Okay, thank you. Anyone else? Brave enough? Here we go.
Can I have a question in Japanese? Can I have a question in Japanese? 大丈夫ですか？すみません。93
You said there was an announcement that you will be go mainnet Q3. When will you go public? And Q2, by the end of June, will you be listed?
So I think the question is about the mainnets in Q3 being listed and so on and so forth. So so my role in the project is that I think I have some insight in blockchain, in what's important in terms of technology, in terms of what's relevant, and so I try to help out the project as much as I can. I pretty much do that full time. However, I'm not involved in actually launching the network or listing or any of that. So I know that the Tezos Foundation is working to launch this network. And yeah, they've announced Q2 for a betanet and Q3 for a mainnet. And the difference between the betanet and the mainnet being that the beta comes with big warnings and possibly maintenance, hard forks, all of the good stuff. Because there's a difference between learning from a testnet, which is less adversarial, and learning for a real live deployed network. So unfortunately, I don't really know about your other question about this, but I can relay the announcement from the foundation.
Okay, thank you.
There's an official announcement on the Tezos Foundation website.
日本語でも大丈夫ですから。
Japanese questions are fine.
分
So distributed autonomous type. So Ethereum, I think this reminds people of Ethereum. So my first question is 60% voting with 60% vote, block governance will change. So is this the 60% of entire token position, or is this the 60% of the number of votes that came in? Which is it?
It's the latest one. It's 60% of a 60%. I think the value is set at it's 60% of 60% now, and these are fairly arbitrary value. It's hard to just do this for the first time and say the right value is 60%, but they are reasonable value. But the second 60%, the quorum, can go down. If so, let's say the first vote. There's only 40% of people who participate, then it will start going down, and at the end you could have a vote that asks for only a 10% participation, in which case 6% of the token could have a vote in this case. However, if it was really bad, then it would only take 5% of all the tokens to counter it.
In that case, so in case of distributed autonomous type, like DAO, is there if there's a bug, or in the adopted governance, if there's an error in the adopted governance, in such a case of emergency, what kind of steps or measures do you take?
Yeah, so that's a good point. The governance mechanism is slow moving. It is not meant for addressing emergencies, right? It's meant for resolving things like block size debates or moving to new consensus algorithms. It's made for debates that can last 6 months, a year. If you have a horrible there's two kinds of emergencies. So if you have a horrible bug that's going to destroy the system unless you hard fork, it's fine to hard fork because that will not be controversial. There's really not I don't think there's a faction that genuinely wants the bug to destroy everything. So if you see a bug like the Bitcoin bug, which lets someone create a billion Bitcoins with an overflow, it's okay to hard fork these things. Where it gets trickier is situations like what happened with a DAO, with Ethereum, or what happened with a parity wallet. Because at that point, you're opening, at that point you're touching contract balances, and you are opening I'm not sure how the translator will translate that, but you are opening a can of worms. So I think they are clear lines of demarcation that could be used. And one line is, have the funds change hands. One way that money is very different from property in how it's treated typically is that if you have a painting and I steal your painting and I sell it to someone, someone honest, they don't know it's stolen, and you find your painting, you can ask this person for your painting back because it's your painting and they have it. However, if I steal your money and I use that money and I go buy myself a movie ticket, I don't know, it's not a lot of money. You cannot go to the movie theater and ask for your money by saying that money you have was stolen from me. So and that's really, really important to have that with money because otherwise it stops functioning as money. Because otherwise every time you accept money, then you will have to know for sure that it hasn't been stolen at any point in its history and it cannot be clawed back. And that basically would destroy commerce. So one line is whether or not whether or not it was a hack, whether or not it was a bug in a smart contract. One important line is, has money changed hands? And if money hasn't changed hands, as in the case of the parity wallets, if you look at the latest EIP, they're not saying like, oh, give us some. All they're saying is like, hey, can we create a contract? And the only change with the rules that they're asking is say, well, we just want to create a contract with a certain hash. It just needs to have a certain hash, nothing else. So, it might seem like if you can really have a very hard line as if the funds have not changed hands, then it might be okay to do something. If the fund has changed hands, even if it's like stolen or so forth, you don't want to touch that. So that might seem like a good line, but unfortunately, even there, I think you're starting to tiptoe too much into having too much influence, and you don't want to be able to have that influence on the protocol because otherwise it can start being the case that you get pressured into doing it, and then people say, well, if you can change this, then you can change that, and you just never hear the end of it. And so I don't think the governance, probably the governance mechanism should probably not be used for that. It's a tricky question because this is essentially an argument from a slippery slope, and there's just not enough history to really know how slippery the slope is. My personal position is that I think I'm on the slippery side. I think it's slippery, and even if it comes at a very great cost to just not go down that slope, it's probably worth it. But it's by no means a completely set question. I think it's an empirical question. I don't know if that answers your question.
どうもありがとうございました。
Thank you very much for that.
I think Tezos is quite well known for collecting huge fund last year, like 300, 400 million USD. How big is your engineering team now working full-time commitment?
There's a lot. So there's quite a bunch of people working on Tezos. There's some people working on Tezos in France. I think that I know of. I know about 12 people working on it in France. I know that there's some people. I think there's 3 people working on it in New York. There are people working on it in Korea, in New Zealand. So I don't know I don't know if those people are working full time or not. But I know full time in France. There's about 10 to 12 people working on it.
That's the number you confirm.
The what is?
That's the number you confirm full time. 10 to 12.
Yeah, that's what about that. I think, yeah.
Okay, thanks.
There's also currently 40 open positions.
So they have an office, and I hang out in the office. So if I do a head count, yep.
Hey Jake, how are you?
First of all, I'm quite encouraged to see that there's actually some local presence here. I met Corey probably an hour and a half ago. He came on to really grow the community here in Japan, so that's very encouraging to see Tezos doing that. I'm kind of curious in terms of your primary itinerary for your visit here in Japan. I mean, besides this event, I was wondering what other activities besides growing the community you might be involved here in Japan specifically?
Yeah, so I was the initial reason for my trip is I was invited to speak at an event yesterday, a TOA Tech Open Air event, and also I was very excited to go to Japan because well, I know that there's a big community here, and so it was like, yeah, I get to meet the community, also see Tokyo. I've never seen Tokyo, so I was happy to do that. And I remember like a few years ago, I was looking at the OCaml, like trying to map the OCaml ecosystem in the world. And as many of you know, Tezos uses OCaml as a programming language. It's fairly academic, and so it's not very well known. If you look at Google Trends, I think Haskell, which is also a functional programming language, is about maybe like 50 times less popular than JavaScript, and OCaml is 20 times less popular than Haskell. But its quality matters, not necessarily quantity. And when I search for OCaml on Twitter, I would find tweets in French because the language was created in France, and so there's a big French community, but also half of the tweets were in Japanese. So apparently there is a lot of OCaml in Japan. I'm going to Kyoto tomorrow to meet a professor at Nagoya University who's also working with OCaml, and so it was both the Tezos community and OCaml community. I also think that for Tezos to be a success, it needs to really be an international project, and that means having people involved in it around the world, and working on the code, building applications, building amendments to the code. And I hope that by visiting Japan, I can meet some of the people who might be doing that in the future, or even possibly inspire people to do that.
Great, thank you. Appreciate you coming and engaging us locally.
Thank you so much for the very informative presentation. I have a question. In one of your slides, you had collaborative or competitive, comparing the two, which is very, very interesting. How do you feel about corporate giants such as Amazon building their own blockchains? Is that more collaborative or competitive from your perspective? And also, a lot of people say that smart contracts was the year 2017, but this year it's interoperability as the key term for scalability in terms of blockchain. I would love to hear your thoughts on both of those questions.
Okay, great question. So what do we think about giants like Amazon building their own blockchains? I think they will have their own use cases, and it's going to be different from having a big cross-border uncensorable blockchain. If you want to have something that works reliably in Venezuela, for example, it might be easier to do that with a decentralized network than with Amazon that can get blocked. And maybe not Venezuela, because I don't think Amazon doesn't necessarily do a lot of business in Venezuela, but there can be government pressure on Amazon as a large business that would not necessarily exist on a decentralized network. And so I think there is a niche that's always going to be there for the decentralized network, particularly to be used for either transactions where you really require a level of trust that you wouldn't necessarily get with a central actor, or circumstances when people live under oppressive governments. So we'll see what Amazon come up with, but right now, empirically, most of the research, most of the brain drain is in public blockchains. Now the question, the whole interoperability thing. So everyone who talks today about, I have a nice theory about it, and I have a cynical theory about it. So the cynical theory about it is that everyone who wants to do interoperability is going to explain to you that they have a coin, and that coin is going to bring interoperability. And I think the reason for that is it's the idea that you're going to compete in this space is a little taboo. It was taboo for a while, especially with Bitcoin, because you cannot, how can you compete with Bitcoin? Bitcoin is the first one, you're just copying the idea, and so on and so forth. And who do you think you are? There's so much network effects, and so on and so forth. And with the growth of Ethereum, I think people have been questioning that the first mover effect of Bitcoin a little more. And also, it's less attractive to people. You say like, I'm going to compete. I'm going for a fight. Who wants to go for a fight? So instead of that, you say, no, we're complementary. It's like, I want to create the N+1 blockchain. Well, it's crowded. There's all of these blockchains. How are you compete with all of that? No, but you don't get it. We're not going to compete. That's the whole thing. We're just going to be on top of everyone else. But it's not clear that everyone else is going to be a vassal of this. So that's a very cynical view. I think it's a way to disguise an attempt at basically being the block. You want to be the blockchain. You want to be the number one, and the way you do that is by trying to bring everyone else underneath you. So that is one thing. I think it stems more from that than from a real need or for a real interest in interoperability. Now let me dive a little deeper. Economics favor one chain, and when I say one chain, it's not exactly accurate. I think economics favor one token. And one very interesting proposal back, I think it was 2014, was the sidechains for Bitcoin. And if you think of sidechains, you might say, well, that's better than governance. Why need to have everyone agree on what to do? So my answer for why do we need to get along, right? Why not have everyone? Well, because if you hard fork, then you dilute your network effects. But if you can port your token from one chain to another, then they're not competing on price, they're competing on supply. Now, supply is a dual of price in a market, and so instead of having price discovery, you have supply discovery. It's wonderful. The difficulty is, we don't have sidechains. And the other thing is, if you want to have a sidechain, you still need to find miners who are going to mine your sidechain. You could merge mine, but if you're merge mining, then you're not really adding capacity to your network. The only thing you're doing is you're maybe trying something else. It's also been historically hard to convince miners to merge mine. Also, if you're just porting existing assets, you don't really necessarily have a reward to give them. Like, they're getting transaction fees, but they can fight for transaction fees. There's a paper from Arvind Narayan on that. So not trivial to implement, and also you don't really have shared security. So among the proposals that there are today for all this interoperability, so there's two that I can think of which are interesting. And there might be more, but I'll talk about two. One is Cosmos, and the other one is Polkadot. So what Cosmos does, and one of the brilliant insight of Cosmos and Tendermint is that consensus is boring. And this came at a time where everyone was like, we're going to do consensus this way and that way. And it's like, no. Let's have something that reduces to PPFT, and we'll have validators, and we'll have finality on every block, and we'll have a very trivial SPV client, because a block is valid if we know who the validators are, and if 2/3 of the validators have signed a block, then it's valid. And just having finality on every block and no forks just make it so much easier to write a node, because you don't have to do any rollbacks. Like, it simplifies everything. And also, one of the insight of Tendermint, which I really like, is, what happens if you have a network split? What happens if China gets disconnected from the US, for example? The Great Wall goes up, you don't have any blocks. And then the network stops, and that's great. It's great that the network stops, because you do not need the network to be live every second of the year. If you have a few hours of outage because someone cut an undersea cable once in a year, you want the thing to stop. You don't want your two chains to grow in different directions and then merge. So this is really, really interesting. That's on the upside. On the downside, I think that this business of really just having big known bounded validators, as opposed to something a little more based on randomly selecting tokens, might lead to something more centralized. So I think it pushes towards a little too much centralization. But it's a great way of cutting the Gordian knot. If you compare that to, say, proof of work, like you have like nice theoretical guarantees. Okay, so this is a thing I really like about Tendermint. And then they have this view of saying, well, now that we have this really neat SPV, it is very easy for us to communicate between blockchains, right? We'll have different blockchains, and then they can move tokens from one asset to the other. We're going to have an internet of blockchain. Now, I don't think that solves the problem that most functions are better served if you have a single token to do them rather than many, many tokens, but you do get some interoperability. What you do not get is you don't get shared security in the sense that if you want to start your own vassal of Cosmos, you still need to go out and find your own set of validators. The other proposal is Polkadot. Well, Polkadot is fairly interesting. So remember how I was describing protocol with an apply function? So what Polkadot does is you have your blockchain, you take your apply function, like really literally your apply function, you compile it down to WebAssembly. And then instead of publishing blocks on your blockchain, you go on Polkadot and you publish, you publish the two hashes, like previous block, next block. You have a Merkle proof of the part of the state that's affected in the first block. You have and then the state has changed, and then you have a proof by like outlining the computation. And anyone can post a fraud proof, and then if you have a fraud proof, then Polkadot will look at this and say like, yep, you didn't do the transaction correctly. So what they do essentially is they separate. This separates the idea of collating data into blocks and validating and the idea of consensus. And the benefit of doing it that way is that you get shared security. So essentially what they're doing is they're sharding, but instead of just sharding over like one known code base where you have like n version of the same blockchain running, they're sharding their blockchain over like possibly different protocols. So that's an interesting idea, but I think my instinct is that it's a little overkill and a little complex, and that so that's one thing, and that interoperability is a little it's a little oversold, partly because if you had a lot of trade-offs between blockchains, like, oh, this blockchain is great for X, this blockchain is great for Y, but they cannot both be great for X and Y, because if you're great for X, you cannot be great for Y. So if you had these trade-offs, then, oh, now you need two blockchains, and now you need interoperability between the two. And there are very, very few trade-offs that exist. The trade-offs that do exist are around consensus, or around latency, throughput, but all of that is not something that gets addressed by having this interoperability. Like the interoperability is about the semantics of your blockchain, and for that you don't really have trade-offs. So I don't see a whole lot of value in making all of these blockchains talk to each other. It's also not like all of these blockchains have like really established use cases, and they're really, really big, and they're not going to be displaced because now every hospital in the world is using hospital chain, and clearly now the only way we can do anything is if we have some compatibility with hospital chain. So if we got to a place where like you had a lot of big established players and you wanted to build interoperability between them, that might make sense. But I think we're still into a land rush where a single blockchain can capture many use cases.
I think we're out of time now.
Oh.
Please, a round of applause for Arthur's presentation.